Welcome and thank you for standing by. At this time, all participants are in a listen-only mode until the question and answer session of today's conference. At that time, you may press star one on your phone to ask a question. As a reminder, today's call is being recorded. If you have any objections, you may disconnect at this time. I would now like to turn the conference over to today's moderator, Ms. Kiana Rains. Thank you. You may begin.
Good morning from NASA's Kennedy Space Center in Florida. I'm Kiana Rains from NASA's Office of Communications, and we are very excited to have you all join us today. We have an incredible panel of experts that are ready to answer your questions about space station research and science investigations set to launch aboard NASA and SpaceX's 27th commercial resupply mission to the International Space Station. SpaceX is targeting today, Tuesday, March 14th at 8:30 p.m. Eastern Daylight Time for the launch of its Dragon spacecraft on a Falcon 9 rocket from Launch Complex 39 Alpha at NASA's Kennedy Space Center. Here to talk with us about some of the research launching aboard the SpaceX Dragon are Dr. Meg Everett, Deputy Chief Scientist for the International Space Station Program, who will discuss a variety of research being done aboard the orbiting laboratory. Mike Bennett and Shane Johnson, who will discuss the Hunchball Clamp Monopod. Dr. Mita Hajime, Principal Investigator for the Tampopo 5 investigation. Dr. Ralph Moeller, Principal Investigator for the Biofilms experiment. Devin Mayer, a doctoral candidate in biomedical engineering and medicine at the Johns Hopkins University School of Medicine, who will discuss the Engineered Heart Tissue 2 study. Dr. Dilip Thomas, who will discuss the Cardinal Heart 2.0 study. And Logan Torres, who will discuss the CAPI-SOR visible system investigation. Our speakers will each provide opening remarks, followed by questions from reporters on the line after each speaker. Your phones are now on mute. To enter the question queue, please press star one at any time. When we call on you, the operator will open your mic so you can ask your question. We encourage you to ask questions to the scientists about their experiments. If we have time at the end, we will take additional questions. About 1 hour after we conclude, you can listen to a replay of this teleconference by dialing toll-free at 888-566-0411 or by visiting the NASA Videos YouTube channel. Again, that number is 888-566-0411. To start off, we will hear from Dr. Meg Everett, who supports the ISS program in providing leadership and support for science performed on the International Space Station. Prior to this position, Meg has supported crew health and performance for ISS and future exploration missions as the principal investigator for several ISS experiments and as the crew health and countermeasure system integrator for the ISS program. Over to you, Meg.
Great. Thank you very much, and thank you all for joining as we prepare for the SpaceX-27 launch. So as you can all imagine, the ISS Research Office loves science, and we are especially excited about science in space. So to start off, just from the highest level, ISS serves as an internationally collaborative orbiting laboratory to advance science in space and on Earth. Over 3,000 experiments have been completed in the last 22 years, and this has resulted in over 500 publications in top-tier journals. So what that means is not only are we doing science on the space station, we are doing phenomenal science on the space station. And researchers from all over the world are reading these articles, and they are citing them in their own research and in their own publications. So before we get into the science to be launched on SpaceX-27, I just want to take a few minutes and recognize the truly incredible feat of carrying out science in space with technical excellence. So the facilities that are aboard the ISS enable gold standard science that rival laboratories on Earth and enable scientific discoveries outside of what is achievable on Earth alone due to the presence of gravity. So on ISS, we can do science without gravity, and we can expand upon the knowledge already available on Earth. And with the help of our commercial partners, we're bringing cutting-edge technology that is just being developed on Earth rapidly to the space station to expand what's already capable. With SpaceX, we can return samples, for analysis on the ground, which adds additional capability to science on the International Space Station. So all of this sounds amazing, and it is also carried out within the limitations of life on the space station. So there's intricate scheduling requirements to preserve samples from launch to return to Earth. And the ISS crew members who do this research do an absolutely phenomenal job with a minimal amount of pre-flight training and a lot of times remote guidance in flight. This is in comparison to our scientists on the ground that spend years and years perfecting their skills in a laboratory. So through all this, you can see that science is hard, and science in space is really, really hard. And it takes a dedicated team to integrate research all the way from pre-launch integration through launch activities, performing the research on space station, and returning these samples to Earth for further analysis in our laboratories here. So back to the science that we'll be talking about here on SpaceX-27. Today's launch will be sending hardware to support approximately 60 new investigations to be carried out on ISS. The sciences supported in these areas include human research, biological and physical sciences, education, and technology demonstrations. And we're very excited to have some of the researchers supporting this science here to talk with us today. So I'm just going to give a quick run through, high level of the science that we'll be talking today, and then I'll pass it off to our phenomenal researchers to expand upon these. So Cardinal Heart 2.0 and Engineered Heart Tissues 2.0 are brought to us by National Labs and National Institute of Health, and these will investigate the effectiveness of clinically approved pharmaceuticals and new therapies to reduce or prevent microgravity-induced changes in heart tissue, as well as improve treatments for patients on Earth. The Capasorb Visible System out of Ames Research Center will demonstrate improved carbon dioxide removal methods using liquid dynamics. The ESA-sponsored biofilms investigation aims to look at microorganisms living on internal surfaces of the space station, and the results of this study will help with selecting materials with antimicrobial qualities for future spacecraft. JAXA's Tampopo 5 investigation uses the XBAS facility attached to the GEM. Here, bacterium and moss spores will be exposed to the harsh space environment and will be tested for survivability and growth. And lastly, the HUNCH program has developed the ball clamp monopod, and this hardware was developed by high school students from Cypress Woods, Clear Creek High School, and Conroe High School, and it addresses the difficulty of positioning video and cameras in microgravity in the middle of modules. So with all of this science, we are really excited for the results of these investigations and look forward to impactful science coming forward on human exploration in Earth and advancing technologies in space and on Earth.
Thank you, Dr. Everett. We will now move to questions for Dr. Everett, and our first question is from Jim Seigel with NASA Tech. As a reminder, to enter the question queue, please press *1.
Question. Meg, I was reading the file online here about some of the investigations that are on board CRS-27, and so you mentioned that there were about 60 new investigations. My interest is in telling my readers what kinds of things are going on in the space station that will result in products or services that they can use on Earth. And so besides the investigations that you mentioned that we have people to talk about today, are there any other that come to mind, investigations among those 60 that will have an impact on people here on Earth? Thank you.
Thank you for the question. So first off, I would like to say that we have a huge book on the benefits of space for humanity, and that can be accessed online. But with that, I'll say that the research that we do on ISS is all intended to both improve not only space life, but space on Earth. So just another example offhand of how we're doing that is crystallization of experiments in space. And here in space, we can grow crystals that are much more uniform than we can on Earth. And this also aids in the development of new drug delivery methods that can be used for cancer treatment. So that's just one other example, but I would definitely gear you towards looking through the benefits for humanity, and that has a whole bunch of other examples and great scientific achievements.
Okay, thank you, Meg.
Thank you, Dr. Everett. Now we will hear from Mike Bennett and Shane Johnson, who helped with the student-led Hunch Ball Clamp monopod project. Mike Bennett is a flight configuration project manager at Johnson Space Center. He oversees Hunch student engineers as they design and create products. Shane is a 2-year Hunch member that is now pursuing his bachelor's degree in mechanical engineering from the University of Texas at Austin. First, we will hear from Mike and then Shane. Mike?
Good morning, and thank you for this opportunity to talk about our amazing students and the products that they present. Several years ago, we were presented the opportunity to design a device that would hold cameras and equipment and place it in a module, such as near a hatch window, and also to allow it to quickly and easily be moved and out of the translation path and things like that. Our students went through the design process, our engineering students, and have actually redesigned a camera chute that is a smaller number of parts that interface with the camera equipment. They went through and designed a clamping system that allows for accessories to be attached to the monopod. And the monopod is actually a commercial off-the-shelf that's been adapted by our students in their design efforts. It also attaches to handrails using additive manufactured clamping system. So we were able to involve students that were in the engineering design areas, students that were in the machining, and students that were in the additive manufacturing. And the end result is a monopod type system that will extend from roughly 22 to 64 inches in variable lengths as needed. And again, allow for the attachment of camera equipment and accessories as needed by the astronauts. And Shane actually is one of the students that worked on this.
Yeah, so thank you, Mr. Bennett. For some context as to where I come in, this project started long before I was involved in the Hunch program. I still remember it clear as day. It was my first day of high school, very first day I walk into my engineering classroom, and my engineering teacher sits us down and presents us the Hunch program. And long story short, that day I made a decision that I was going to have something I made on the ISS. And so, again, long story short, I run through the gauntlet of engineering classes, eventually make it into the Hunch program, and that's where I'm presented this project. Previously, a different version of this project called the ball clamp foot restraint, which uses the same ball clamp design but in a different application, was presented to me and my partner Matthew Rubis, and we had invaluable feedback from astronauts on the previously flown model, specifically regarding the thumb screw that was used to tighten down the variable friction ball clamp. Long story short, the astronauts, or the previously flown model, had a square keyhole at the top of the screw for the astronauts to use a tool to tighten it down. They did not want to use that tool anymore, and so Matthew and I were tasked for redesigning this thumb screw to be able to have it more turnable, so to speak, with just the fingers. So we went through the entire engineering design process and tweaked a lot of different things, just basically trying to maximize the surface area to increase turnability. And from the iterative design process, we got to a point where our final product was basically the astronauts were able to turn it almost a whole turn and a half with just the use of their fingers and no longer having to use the tool that was required previously.
And Shane and his partners did amazing work. In fact, all our Hunch students have, whether they're the machining students whether they're the additive manufacturing students or, as Shane, engineering design students, going through multiple iterations to provide a very useful device for using for all the video equipment and the purposes it'll be used for.
Thank you, Mike and Shane. We will now open it up to questions for Mike and Shane. Our first question is, what are the elements and processes that went into manufacturing the ball clamp monopod?
Again, it's multiple elements to it. For example, the ball clamp itself is a combination of additive manufacturing, but it also uses the thumb screw that Shane and his team also worked on, which then was manufactured by our manufacturing school, actually machined out. So there's a lot of different iterations, a lot of different things going on, a lot of design work, and as Shane will attest to, a lot of iterations and prototypings and fine-tuning to go into the final result, the final product. And the great thing about it is this was done with students really across the country, whether it was our additive manufacturing school, our camera shoe school, which was in Conroe, Texas, just north of Houston, or in the Cypress, or in the Clear Creek School District also, near NASA Johnson Space Center.
Awesome, Mike. Thank you. Our next question is, what are some of the examples of changes in students' attitudes towards the application of math and science based on their experience in Hunch?
I think what I've seen throughout the years is I can do this. It's a increase in their confidence. They get exposed to real world, whether it's designing or manufacturing, whatever it may be. This is a real world event to be really used. It's not just an exercise to be used. So they all of a sudden they can see they can do this. They present to NASA mentors, NASA subject matter engineers or experts. So it's quite a change. They go from I can't do this to gaining confidence, and really I think it helps them achieve. Shane can perhaps speak more of that since he's been through the whole process.
Absolutely, yeah. Thanks, Mike. 100% agree. Coming into it initially, it was definitely a very daunting process, but an exciting one at the same time. And so now looking back retrospectively, I'm super thankful for the opportunity to work on this industry grade level project that's given me so much invaluable experience that has set me up very well for what I'm doing now and what I'll continue to do in my engineering career.
Awesome. Thank you, Shane and Mike. Next, we will hear from Dr. Mita Hajime, who leads JAXA's Tanpopo 5 investigation. Dr. Hajime received his PhD from the University of Tsukuba in 1999 and is currently a professor at Fukuoka Institute of Technology. Mita?
Yes, thank you. My name is Mita from Fukuoka, Japan. Now here, Japan is midnight. So the Tanpopo mission is a series of Japanese astrobiology experiments using the International Space Station. The first Tanpopo was launched in 2015. Exposure and capture experiments are conducted almost every year. This is the fifth mission. Astrobiology is a scientific field that studies the origins and distribution of life in the universe. In particular, the Tanpopo mission investigates the chemical evolution and the transport of life in the space environment. The exposure experiments will be carried out on a platform called EX Earth on the Japanese exposure facility of the ISS. 7 small reaction vessels will be installed, and 4 different exposure experiments will be studied. One is nucleotide synthesis by cosmic UV irradiation in the aqueous solution. The second one is the direct space exposure of radiation and UV resistant bacteria to the space environment. direct exposure means we don't use windows material and no cover for the bacteria. The third is space exposure of moss spores. The spongia will protect the spore from the stress of the extreme environment. The fourth is the UV dosimeter using aluminum film because the short wavelength cosmic ultraviolet radiation is thought to make the most significant contribution in the above experiment. Peptide formation in the space environment is also studied using this dosimeter. Thank you.
Thank you, Dr. Hajime. Our first question is, what is the highlight of this Tampopo 5 mission for you?
Thank you. Nucleotide is one of the most important material for life. So, is nucleotide able to synthesize in the space environment? Nucleotide is one of them. So, it is an important question that nucleotide can synthesize in the space environment. And this is the first experiment, cosmic UV radiation to the aqueous solutions. Aqueous alteration is a key step on the small body. So this experiment is, we think, important. And previously, some exposure experiments with bacteria were studied. In these experiments, bacteria were covered with windows. The windows shielded extreme short wavelength UV. But this time, we are not covered by the window. We are exposed directly. That's our highlights.
Thank you, Dr. Hajime. As a reminder, to enter the question queue, please press star 1. Our next question is from Ken Kramer with Space Up Close.
Hey, thank you for doing this. I have a question about how many of these experiments are you planning? How long will they be out there? Do you have the ability to swap them out? And I didn't quite hear, what was the type of radio-resistant bacteria that you were using? Thanks.
This time, half-year exposure is planning. And in this time, just 3.5 years experiment, but in the first Tampopo mission, total 3 years exposure was studied. And using the bacteria is Deinococcus radiodurans.
All right. Could you just repeat the name of that bacteria? I didn't quite get it, or maybe somebody could send it to us. Thanks.
Deinococcus radiodurans.
Okay. All right. Thank you.
Okay.
Thank you. Thank you, Mita.
Thank you.
We will now hear from Dr. Ralph Moeller. Dr. Moeller is a microbiologist at the German Aerospace Center in Cologne, Germany, and is the principal investigator for the biofilms investigation. He is the head of the Aerospace Microbiology Research Group at the Institute of Aerospace Medicine. His team studies biofilm formation of microorganisms on the space station. Dr. Moeller?
Hello, good afternoon from Germany. It's a great pleasure for me to be involved here in this project and also to tell a little about what we are doing. So my name is Ralf Möller. I'm a microbiologist at the German Aerospace Center, and together with my colleagues, we work in a very interdisciplinary project. So I'm a microbiologist, but in our group, we also work with material scientists. In our project Biofilms, which is led by the European Space Agency, we are interested in the microbial biofilm formation. So as you know, all on our skin and our body and in the environment, we have a lot of microorganisms, and they could cause different kinds of problems. One very visible issue is a microbial biofilm. So sometimes you see a kind of a slime or like a kind of like dirty, ugly structure, and then this could be associated to microbial biofilms. In space, we have different kind of conditions, especially inside the space station. So we have microgravity, we have a higher radiation exposure, and we have a unique environment. So if you consider the space station as a habitat which is now in operation for more than 20 years, and we have microorganisms causing problems there, and we don't know how they flourish, how they grow, and what kind of material damage they cause. So this was the origin of our experiment. And biofilms, which is a free stage experiment, and currently we are in the last phase. So we're sending to space 3 different kind of microorganisms. So one microorganism, which you're probably familiar to, is Staphylococcus. So it's microorganisms from the skin. And the other organisms are Acinetobacter and Cupriavidus. Both have been associated and isolated from space environments, one from a water pipe system and one from a Mars rover before it was cleaned and sent off to space. In the experiment, we are testing the biofilm formation on unique surfaces. And here we are using the material science features and attributes of laser structuring. So really in biofilms, we're addressing the point, how could microorganisms attach on a surface? And with new technology like ultra laser interference patterning, we are designing surfaces with different kind of grids and stranches and surfaces, which maybe makes microorganisms unable to attach. On the other part, we're also looking at chemical features like different kinds of metals and ions. For example, we're comparing steel with brass or copper. And the idea is, using all those data, in the end, we could tell what kind of microorganisms maybe humans leave in the space station, how biofilm formation is done under microgravity, and maybe what kind of future materials can be used to address this part for future space habitat station design. And this is part of the biofilms. I'm very happy to report this here.
Thank you, Dr. Moeller. Our first question comes from social media by Kaustav Dasgupta on Twitter. Is the study of bacterial metabolism more dynamic in microgravity than on Earth, as they consistently increase biofilm formations?
Very good question. Thank you very much. What we know is that the microorganisms adapt to microgravity, and one very fundamental process is nutrient metabolism, so all the physiology. We see the same with astronauts. They're changing, have different physiology changes under microgravity conditions. And with microorganisms, we know from a couple of previous experiments, including space shuttle experiments, that the biofilm formation is different. So we're talking about different arrangement, different architecture, different morphology. And the idea is, if we're using novel antimicrobial materials and structures, is this changes in the space conditions leading to higher or less biofilm formation? And this will be investigated within biofilms.
Thank you. Our next question is from Jim Seigel with NASA Tech.
Hi again, and thank you for taking my question. Dr. Muller, you mentioned the importance of trying to mitigate various problems on the ISS based on these microbial films, and I'm curious about whether there have actually been problems that the astronauts or others have identified, real problems on the ISS that this investigation will attempt to remedy. Thank you.
Thanks, Jim. Great question. There have been reported a couple of issues, and some of them have been directly associated with microorganisms actually flourishing. So we're talking about water pipes. So there have been a lot of recycling of air and water, and here microbial biofilm formation has been shown. And if you think about a life support system, we have to maintain also the operation of a life support system or a recycling system. So there have been some reports on clogged pipes and biofilm formation leading to material degradation. Also, it has been reported from previous experiments, for example, on the Mir station, also on the ISS, that on different kind of panels where you put your towel or you put some moist or liquid, anything on top of them, biofilm formation can be seen. And here, of course, we are interested not just to see if the microorganisms are persisting on the surface, but maybe also what kind of material and damage are they causing, for example, in electrical wires or something like this. So yes, there have been some reports, and I think for future space station, we have two choices. Either we could clean surfaces, or we could help also to mimic or reduce the effect of microbial attachment.
Yeah, good explanation. Thank you.
Our next question is from Ken Kramer, Space Up Close.
Thanks again for doing this. Take my question. Yeah, I'd like to know a little bit about the mechanics of how you're going to go about doing these experiments. Are you taking samples over time? Are the astronauts taking photos over time? Is it just at the end? And where are you doing the experiments to, please, like the modules?
Thanks, Ken. Also, great question. So we're doing the experiment in a little incubator called Cubic. It's an incubator, and there we have different kind of different sample containers. And in the sample containers, we have a specific type of microorganism with a specific type of media, and then we have specific surfaces. So the idea is to run the experiment under different gravitational conditions like microgravity or Martian gravity, and also having a 1G Earth control with the incubator. And then we are mimicking the surface conditions, like the temperature, like the average ISS conditions. Then we are testing different kind of materials in these little containers. We let the microorganisms grow under optimal conditions, and then we get the samples back. And once the samples are back, for example, in our facility at the German Aerospace Center, then we do a thorough microscopy analysis. We are checking what kind of material damage have been seen, if they're getting ion released from the materials, and also we're looking on biofilm thickness and stability and all those regards. So we will bring the samples to space. We get the samples back. Afterwards, we get the samples back. We do the post-flight analysis.
So there's no sample taking or photos during the time they're in space. Is that right? It's just at the end you get the box back?
Yeah, we got in the end, we got the containers back, and we have a total of 72 containers in space, so it will be a real lot amount of crew time. So in here, with the Cubic device, we could test different kind of conditions under different umbrellas. So we have also samples without microorganisms, samples with specific kinds of laser-structured materials. So in the end, if we would have an astronaut doing all these experiments, it probably would take a lot of crew time. So we very much appreciate getting the samples back and doing the sample analysis on ground.
All right, thanks. I think it would be interesting if you could mimic that towel experiment at some point, maybe. Thanks.
I appreciate it. Next time.
Thank you, Dr. Moeller. Joining us next is Devin Mayer, one of the principal investigators for the Engineered Heart Tissue 2 investigation. Devin is a doctoral candidate at the Johns Hopkins University Department of Biomedical Engineering. Devin has authored or co-authored 9 journal articles and has won numerous awards for his research. Devin?
Hi, thank you very much for the introduction. I'm very excited to talk to you all today about the work I've led in the lab of Dako Kim at Johns Hopkins University about the effects of spaceflight on the heart. So the human body is an absolutely amazing machine with countless mechanisms to respond to negative environmental stimuli. However, there are unique stresses found in spaceflight that offer exceptional challenges to our bodies, which they can struggle to overcome. One of the most significant of these challenges are the hazardous effects of spaceflight on the cardiovascular system. Previous human and animal studies have verified that exposure to microgravity or the apparent lack of gravity as found on the International Space Station can lead to a variety of cardiovascular problems. This can include decreased cardiac output, loss of cardiac muscle mass, and serious cardiac arrhythmias. This in turn can lead to severe consequences for astronauts, including increased risk of heart disease and stroke. So in order to develop a deep understanding of the effects of spaceflight on the cardiovascular system with an eye on identifying mechanisms to prevent or treat the negative effects of spaceflight, we in the Kim Lab launched human 3D engineered heart tissues to the International Space Station for 30 days in 2020. Our system was engineered from the ground up to limit astronaut time requirements. It consists of an engineered heart tissue fabricated between two posts, one flexible and one stiff. When the heart tissue beats, it moves the flexible post. We embed a magnet in this flexible post, and in space, we position our tissues above a magnetic sensor. This allows us to acquire real-time data on tissue health for the duration of the spaceflight mission without requiring significant astronaut time or resources. In our study in 2020, we found numerous signs of heart failure. Digging deeper, we identified many important biological structures and processes that were negatively impacted by spaceflight, which could lead to this downstream tissue-level dysfunction. One of the most important of these was indications of mitochondrial dysfunction. Mitochondria are especially important for the energetically demanding processes involved in keeping our hearts beating. Also, outside of this well-known role as a powerhouse of the cell, mitochondria play key roles in a wide array of cellular processes, such as the regulation of inflammation, stress response, and cell death, among other functions. Importantly, mitochondrial dysfunction is also a key instigator of many forms of heart disease on Earth. After studying the effects in our first spaceflight mission, we are now launching more engineered heart tissues to the ISS with a variety of therapeutic strategies we are hopeful will prevent or treat the negative effects of spaceflight. This is an increasingly important problem for us to address as we eye longer duration space missions such as the Gateway Outpost, the Moon Base Camp, or future deep space exploration missions. However, our research is not only important in the context of spaceflight. Numerous studies have informed us that the negative effects of spaceflight closely mirror the effects of aging here on Earth. Therefore, this research is not only critical for the future of space exploration, but also critical for the health and well-being of people here on Earth as we try to better understand and combat the effects of age-related cardiovascular dysfunction, a leading cause of death in the United States. And so that will serve as my introduction for the years of hard work we have put into this project, and I'm happy to take and answer any questions there might be.
Thank you, Devin. Our first question is, what are your hopes for how the results from this experiment will be applied?
Well, of course, we're extremely hopeful that we actually do treat the negative effects of spaceflight on the heart and that this will have impacts for future space exploration as well as aging here on Earth, as I've already mentioned. So really, the best case scenario is we find something that can be used to enable these future spaceflight missions and also help prevent heart disease here on Earth.
Our next question is from Jim Seigel with NASA Tech.
Hi, and thank you for taking my my question, Devin. I'm interested in your goal of trying to understand how the investigation might affect the treatment of cardiovascular disease on Earth. I wondered if you had any specific findings that have been applied to processes in the medical community here on Earth, and if not, what sorts of things might the medical community benefit from, such as you're going to tell them about new pharmaceuticals or new techniques for understanding atrial defibrillation or whatever. Do you understand my question?
Yeah, thank you, Jim. So give me one moment to collect my thoughts on that. So basically, how can our findings be applied to people here on Earth, and what do we actually hope will come out of this in terms of treatments for heart disease here on Earth? So interestingly, one of the key ways that NASA has already implemented to try to prevent these negative risks of heart disease and cardiovascular dysfunction in astronauts is exercise. And exercise is already very much prescribed here on Earth for improving heart function and heart health as people have aged. So that is one of the indications that that the outcomes we find in space can now also be applied here on Earth. So we are very hopeful that right now we have tried numerous pharmaceuticals that are being sent up to the International Space Station right now, that we are hopeful can also help to prevent a lot of these age-related cardiovascular dysfunctions, including atrial fibrillation and other heart diseases. Does that answer your question, Jim?
Partially. Let me ask you this. So the pharmaceuticals, for example, are we talking about results that could be applied on Earth, say, in a year, in 5 years, in 10 years? Would you hazard a guess on the time frame that might be involved here?
So all of the drugs and pharmaceuticals that we are testing on the International Space Station are FDA approved currently. So theoretically, they could be applied as soon as our results come in. However, I would, of course, want to caution that these are, while they are human heart tissues, they are neglecting the effects of other tissues in our human body. So while the results might be very interesting and could eventually lead to treatments for age-related cardiovascular dysfunction here on Earth, there obviously needs to be further studies, especially human studies, to confirm the results in a full systemic model rather than just an isolated heart tissue.
Okay, good point. Thank you.
Thanks for the question, Jim.
Thank you, Devin. Now I apologize. We have one more question from Nicoletta Lancy at Live Science. Nicoletta, go ahead. Okay. We will try Nicoletta again a little bit later. Now we will hear from Dr. Dilip Thomas, one of the principal investigators for the Cardinal Heart 2.0 investigation. Dr. Thomas is an instructor and NIH Fellow at the Cardiovascular Institute at the Stanford University School of Medicine. His area of expertise is the cardiovascular biology, tissue engineering, and stem cell biology.
Thanks, Anna. So we at the Stanford Cardiovascular Institute in Dr. Joseph Wu's lab are leading several novel investigations to understand human heart diseases. And space effects on the heart, be it cosmic radiation or microgravity, is one of our major research areas. Speaking specifically regarding microgravity, what we know from previous studies is that microgravity and weightlessness causes tremendous mechanical stress to the heart muscles that pump blood. And at a cellular level, this stress can eventually reduce the strength of the heart muscle, leading to symptoms that are similar to patients that suffer from heart failure on Earth. So our model is derived from stem cells that we grow in the lab, and it's very simplistic in nature. But it can recapitulate fundamental properties of the cells of the human heart. Our current investigation, dubbed Cardinal Heart 2.0, is a sequel to the previous study that was launched to the International Space Station on SpaceX's CRS-21 mission. In this observational study, we utilize engineered heart tissues or cardiac muscle strips that beat spontaneously. In that experiment, we observed several changes in function and gene expression after 4 weeks of microgravity exposure. And as I mentioned before, these long-term, these changes may have a detrimental effect on the heart function. So the Cardinal Heart 2.0, launching on SpaceX 27, is more of an interventional study that builds on this knowledge from SpaceX 21, where now we are sending about 3,800 heart organoids to the International Space Station. So these are roughly 20 times smaller than the model that we flew on CRS-21. So in this study, we take a preventative approach by treating the cardiac organoids with FDA-approved drugs before even they take flight. And what we hope to see is that the negative effects we observed at a cellular and a tissue level in our previous study will be limited, if not completely reversed. That's all.
Thank you, Dilip. We will now take questions. Our first social question is, why are these kinds of experiments done in a weightless environment?
So one of the main advantages of using International Space Station as a platform is that based on several studies that have been conducted, it appears that cells go on a very accelerated aging timeline in a microgravity or a weightless environment. And that helps us understand human diseases that might occur after a long period of time, but much on a faster scale. But having said that, there are a lot of caveats in these kind of studies where it's not an entire organism. Instead, it's just a small surrogate of a particular tissue, such as heart, lung, liver, or brain, that gives us some idea whether these cells can identify that weightlessness or mechanical unloading stresses in an environment like the International Space Station. So it's digging more deeper at a cellular level, how the cells sense their environment and how they respond to external stimuli and drugs.
Thank you. Our next question is from Jim Seigel with NASA Tech.
Oh, hi again, and thank you for taking my question. I just wanted to clarify the mechanics of this investigation. So you've got 3,800 samples, let's say. They have been treated with pharmaceuticals that have already been developed. And so they're going up to the space station, and the idea is to understand whether these pharmaceuticals are effective on these samples. And so not only for space flight and the astronauts, but also back on Earth, because the microgravity kind of mimics aging of people here on Earth. Is that correct? Did I get it right?
Yes. Thanks for that question, Jim. Yeah. So what happens with aging is that your muscles weaken with time, a process we refer to as atrophy. And that's similar for any muscle, it be the skeletal muscle or even the heart muscle that's pumping continuously. So that weakening of the heart muscles is mimicking a condition called heart failure, where patients on Earth could suffer from, and that weakening of muscles could eventually lead to a complete total failure and could prove fatal. So the drugs that we are treating are, it's a combination of drugs that are targeting that particular disease by modulating certain biological pathways that we want to intervene to slow down or to even limit the damages that occur due to that effect of weakening of this contracting muscle cells in the heart.
Okay, so the idea here is, with all these pharmaceuticals that are being used on these samples, to identify the pharmaceuticals that are most effective on the space station and possibly on Earth. Is that correct?
That is correct, yes. So from the first mission, we received some samples live back on Earth, and on those samples, we tried a variety of different drugs to see which one helps in improving the function of the heart muscle strips that we had sent in 2020. And based on that screening, we selected the top two candidates, which are now being flown on the SpaceX-27 mission.
Okay, two of them. Okay. Thank you.
Thank you, Dr. Thomas. Finally, we will hear from Logan Torres, who helped to develop the CAPI-SORB visible system experiment. Logan is an engineer at IRPI in Wilsonville, Oregon, and he supports development and design of capillary fluidic solutions to low-gravity thermal fluid systems. He is joined by Grace Balancic, Air Revitalization Lead for Ames Research Center. Logan?
All right, thank you. Really excited to finish this off today, get to talk about the CAPI-SORB project. So to start, I'll give a little bit of background on the project. So our team is currently developing a new carbon dioxide removal system that will employ a liquid sorbent to absorb CO2 from recycled spacecraft cabin air. The International Space Station currently has two different CO2 removal systems that have worked well for many years, but NASA is always looking to advance their life support systems for future spaceflight missions, whether that's increasing the reliability or decreasing the maintenance and power and mass requirements. So our team has set out to tackle some of these performance enhancements. So the CAPIZORB system uses a liquid sorbent to capture CO2 directly out of the air. The liquid that we use readily absorbs and holds CO2 at room temperature, but then releases it once it has been heated. So we can create a continuous closed-loop system by first exposing a large surface area of the liquid to the cabin air at room temperature, collecting all that liquid and pumping it into a heated container called a degasser, where the CO2 is driven off and dumped to downstream processing systems. And then we cool the regenerated liquid back to room temperature, regenerate it with some water, and then we expose it for more CO2 capture. And that continues in a closed loop. So submarines have been using this approach for many years, and they expose the liquid to the air by spraying it into a chamber and allowing all the liquid to settle and collect at the bottom of a tank. And then they pump that liquid out for regeneration. However, in a spacecraft, there's no bottom of a tank because there's no settling or gravitational forces to collect all that liquid. So we employ a different approach, which is to spread out the liquid into a large, thin, stable film. And this film is produced by branching and bifurcating the liquid out into thousands of capillary channels, which have an open interface, and that allows direct exposure of the liquid to the air. And the channel geometry is designed such that capillary forces provide stability and control of the film, kind of like the bottom of a tank. But they also allow us to passively pump the liquid across the channels to refresh the liquid film, providing fresh liquid for CO2 absorption. So this experiment that's launching is a demonstration of the capillary-based fluid control mechanisms, which have been developed over many years of large length-scale capillary research, both on the ground and in prior spaceflight experiments. So this experiment, we won't be doing any major CO2 transport because we're going to use a stimulant liquid in place of the real sorbent. It'll have similar fluid properties. But every other aspect of the system is going to be demonstrated, whether that's bifurcation of the flow into hundreds of capillary channels, transport of that liquid across the channels via surface tension, wetting characteristics, and geometry. We would demonstrate stability and control of the liquids against large perturbations and varying fluid properties, as well as some multi-phase water management, such as like condensation and collection of water vapor that occurs in the degasser. So all of the data that we acquire from this experiment, whether that's the stability limits or the mass balances, momentum models and thermal models, will inform our design for the full-scale CAPIZORB system, which is currently being developed on the ground at Ames Research Center and here at IRPI using the real liquid sorbent. And so with that quick overview, I'll take any questions you guys have. Thanks.
Thank you. We'll now take questions for Logan and Grace. As a reminder, please press *1 to enter the queue. Our first question is, what are some other applications of this technology, either inside or outside of NASA?
So there are definitely lots of applications. Even here on Earth, CO2 capture is a hot topic in general, and so the research that we put into developing and optimizing the system and the sorbent that we're using could be used to enhance CO2 capture systems here on the ground as well as for systems for future spaceflight missions.
Thank you, Logan. We will now take additional questions for any of our speakers. Again, if you would like to ask a question, please press *1 on your phone to enter or re-enter the queue. Our first question is for Dr. Mita Hajime.
Yes?
From social media. From Stevens Universe on Twitter. What are the risks of human contamination of other planets, and how can the Tampopo 5 investigation inform strategies to protect them?
It's a good and discussed question. The our experiments show the survivability of microorganisms. So at least from us to the other planets, the many satellites will go to the other planet. It is in the cases it's easy to survive the terrestrial microbes on the satellite. So the estimation of the survivability is used will our result will be propose some survivability of our terrestrial microbe on the space. Sorry, difficult.
Thank you so much, Mehta.
Yes.
Our next question is from Jim Seigel with NASA Tech.
Hi, just kind of a follow-up question for Meg. I believe you mentioned that there are around 60 new investigations going up on CRS-27, and I wondered if there was a list somewhere of all of those 60 investigations, of course, in addition to the ones that we've talked about here today. Thank you.
Hi. Yeah, I'm sorry, but we do not have a publicly available list for you. We could try to pull a couple together if you have a specific interest that you're looking for, but at this point in time, we don't have anything that we could send out.
Okay. Well, as I mentioned before, I'm particularly interested in those investigations that might have some application back here on Earth, and I'm particularly interested in food production and any additional investigations that are going on that might eventually be able to be used by farmers or other people here on Earth. Thank you.
Sure. I don't have that list here offhand, but we can get you a list of those investigations with some publicly available information and pass that along to you.
Oh, okay. How do I do that?
We'll follow up with you. I believe we have your contact information from the call.
All right. That's great. Thank you.
Thank you. Our last question is from Ken Kramer with Space Up Close.
Hi, thank you for doing this. A couple of quick cargo questions. One, just to follow up on what you just said. Usually the ISS National Lab has a list of experiments, so if you could make that available, if they have any on this, that would be really helpful. The other questions I have is about unpressurized, looking at the mission overview. I'd like to know what unpressurized payloads are on this mission. I'd also like to know what spacewalk equipment that is going on this mission. And can you tell me when the next set of solar arrays are going up? Thank you.
All right. I will try to tackle all of those questions. I may need you to repeat them, though, in order.
Okay. Sure.
So first off, for the National Labs experiments, we can get you a list of those, and we have your contact information, so we will pass that along to you. For the spacewalk hardware going up, we do have an EMU being launched on this vehicle, and that will be used in future EVAs. Can you remind me of your other questions?
Yeah, any further detail you have about that EMU would be really helpful. I'd like to know if the unpressurized payloads, you're listing about 1,100 pounds of unpressurized payloads. Maybe that's in the trunk. I'd like to know what those are. And the last question was about the next set of solar arrays. When are they going up? Is that on CRS-28 or what mission is that? Thank you.
So to answer your first question on the unpressurized payload, we do have STP-H9 going up on this vehicle. that is in the trunk, and it will be deployed in the GEM module. For expanding on the EMU, I can try to get additional information, but from what I know, there's nothing special about this EMU. It will just be there to support the current fleet that we already have on Space Station, and these are fit to the crew, so the EMUs are flown for each specific crew member. Lastly, on the solar arrays, I probably need to get the information for you to clarify what flight that is going on and whether or not that's publicly available quite yet.
Thank you, Meg. Thank you all for your interest in the important science, research, and technology launching aboard the SpaceX CRS-27 mission. You can follow all the research being conducted during Expedition 68 and 69 by visiting nasa.gov/station research news or following @ISS Research on Twitter. Stay tuned to nasa.gov/SpaceX for regular updates in advance of the upcoming launch. We are targeting this evening, March 14th at 8:30 p.m. Eastern Daylight Time for launch. Launch broadcast coverage will begin at 8 p.m. Eastern Daylight Time. As a reminder, you can listen to a replay of this teleconference by dialing toll-free at 888-566-0411 or by visiting the NASA Videos YouTube channel. Again, that number is 888-566-0411. Thank you all for joining us. This concludes today's call.